No. Wow. Okay, is it all out of your system now? You guys all got it all? Everything you had to say? Everything's out of your system. All right, here we go. So, here's this, my best attempt at a circle here. Something like that. Okay. So using our meaning for, what's our meaning for sine theta? What's our meaning for sine theta? Let's see here. Diana, did you get sine theta? Why is it that? Based on our meaning of sine theta. Why'd you do that? No, it's what we've been talking about for the last month. It's not flipping through your notes. No, not opposite over hypotenuse. Christopher. Vertical distance is a fraction of the radius length, right? Sine theta for this point A is our vertical distance above the horizontal diameter. In what unit? Fraction of the radius length. What's our radius length? 11.88. So you're going to take whatever that height is. If you take it as a fraction of the radius, that gives us, we know what the output of sine is. Vertical distance above the horizontal diameter in fraction of the radius length. Okay, cosine theta. Cosine theta. Derek. Why? He said because that's the horizontal distance to the right of the vertical diameter of what point? Of what point? Okay, but it's really, so we sweep an angle, it's really the focus is this point here. Right? So if of this point, it's the horizontal distance, you said, to the right of the vertical diameter, measured in? Fraction of a radius length, right? And 11.88 is still the radius. So we want this fraction, 10.62, of 11.88. That gives us this horizontal position, which we know is our cosine. Tangent theta. What is tangent theta? Ashley? Because? Okay, so the easiest way to see this here, we had two different meanings for tangent. Easiest in this picture is to see is the slope of the terminal ray, or the slope of CA will be change in y over change in x. The change in y over the change in x is the slope of CA. Okay, so one more time. If this is our angle theta, then there's two legs. Okay, there's two legs of the triangle, the ones that form the right angle. One of them is next to theta, so we call that the adjacent side. One of those legs is across from theta, so it's the opposite side. And then the radius of the circle is the long side of the right triangle, so it's the hypotenuse. So sine theta turns out to be, because it's the vertical distance of point A above the horizontal diameter, it turns out to be opposite over hypotenuse. And cosine is adjacent over hypotenuse. And tangent turns out to be opposite over adjacent. So these, using the triangle, that's not where sine, cosine, and tangent theta come from. Where sine, cosine, and tangent come from is what we've been dealing with the last month. As a result of those meanings, horizontal distance is a fraction of the radius, vertical distance as a fraction of the radius, slope of the terminal side. As a result, then, when you apply a triangle, these are the relationships that you get. So this is the result. It's not the definition. It's not where we start. It's just the result in right triangles. Okay, so some old hippie caught another hippie tripping on acid. This is how you can remember it. SOHCAHTOA. Old school SOHCAHTOA. Okay. So this guy, however you want to remember it, okay? So however you can remember it. Let's see. So then let's look at, make not too big a mess of this. Consider this angle then, right here. So I'll start doing the red. Hopefully this won't make too big of a mess. Consider this right here, angle alpha. So I'll make a new angle in that triangle. And I'm going to attempt to let's see. Now A is the center of the circle. Okay, here we go. So watch this. A little flat, but you got the idea. Okay, so you can make another circle where alpha is that. So A now is the center, okay, and CA is still the radius of that circle. Can you see it? So now, what would sine of alpha be? So can you see that now this is like horizontal diameter is this way, and vertical is turn it on its side. So turn this whole thing on its side. Angle alpha being swept from the horizontal. Can you see that sine alpha would be, this would be the vertical height, right? So for alpha, this is the opposite side, and this is the adjacent side. So this 5.33 would be about horizontal position relative to alpha, okay, or cosine. So sine alpha would be 10.62, its opposite side over it's 11.88. Measuring this vertical, so you got to think of this as now the vertical position above the horizontal diameter, which goes this way. So it'd be 10.62 in radius lengths divided by 11.88, but it's still opposite over hypotenuse. Do you see that? Because now 10.62 is the opposite side to alpha, and the adjacent side to alpha is 5.33. So cosine of alpha is the 5.33 over 11.88. So it still works, but now when you look at alpha, the opposite side is now, instead of being 5.33, opposite of alpha across the triangle is the 10.622. 10.62. And then the adjacent side to alpha, next to alpha, that's the 5.33. So cosine of alpha would be a 5.33 over 11.88. Okay, so go on to the next page. Any questions on that? And look at this, number 5. Okay, it's kind of hard to read. This says 6 centimeters here in your book. Yeah. And this is 2. So without finding the angles alpha and beta, determine all these trig functions. Sine alpha, cosine alpha, tangent alpha, etc. Sine beta, without finding the measures of the angles. Go. Okay, Devin, sine alpha. Nice and loud. He wants 6 over square root of 40. Is that what you said? Agree? Cosine alpha. Colton. Tangent alpha. Braden. 6 over 2 equals 3. Simplify if it's super easy to. Sine of beta. Let's see. Yeah.
2 over.
Cosine of beta. Some people over here. Evelyn. Tangent of beta. Jessica. Or? Okay, questions on those? Does it make sense? Okay, so how could we find alpha? Any ideas? Mitchell? Okay, so if we've got sine of alpha is 6 over square root of 40, so what do we have? We have vertical distance over horizontal diameter, or we have the output of sine, we want the input of sine. What function will give us that? Arcsine. So the nice thing about this is If you imagine, okay, so if you imagine here's alpha, here's our angle swept counterclockwise from 3 o'clock. So here's our y-axis. And here's our x-axis if we're using inverse sine. What quadrant are we in? We're in the first quadrant. So, and we know the output of arc sine is in what range? What range of angles? Is 0 to pi over 2? Negative pi over 2 to pi over 2. So that the range of this is from, sorry, it's not arc sine of, you don't put an angle in, right? Arc sine of okay, and so we know the range is from negative pi over 2 to pi over 2. And so with these triangle problems, you're kind of like always in the first quadrant. Okay? So we don't have to really worry about these issues of having to like mess with your answer to get the right angle that you want, because the right angle that you want is for these right triangles is virtually always in the first quadrant. Is that true? Yeah. Okay, so what do you get when you do that? Anyone did it? Nice and loud? 1.25. Does the number make sense? Looking at angle alpha, 1.25. Do you look at that and say, yeah, that makes sense? Do we have to put it in degrees? We could, but does it make sense as it's just 1.25?
Yeah.
Why, yeah? This is what degree measure, or what angle measure? It's radians. Radians measures radius length, right, of arc length. That's the value. So about 1 radius length is about there. Remember? And so does it make sense that our angle is about 1.25? Yeah, it's like 1 1/4 radius length cut off by that angle. So let's go ahead and find degrees. 0.6? 71.6 degrees. So now finding beta, you got two choices. You can use an inverse trig function again on one of these sine beta, cosine beta, tangent beta. Or you could. The sum of the angles in a triangle is 180. You got 90 taken care of here. So these two, the two acute angles in a right triangle sum up to 90 degrees. So what is this? 18.4? Did I do that right on the fly? 18.4. So yeah, so the two smaller angles sum up to 90, or you could use, arc cosine, arc sine again to find beta. So the relationship between the three sides is your Pythagorean theorem. If you have any two sides of a right triangle, you get the third by Pythagorean theorem. The relationship of the three angles is they sum up to 180. Have any two angles, you get the third. Okay, by that relationship. Questions on this? Okay, so this triangle, trigonometry is really, the word trig comes from triangles, okay? So this is really useful stuff in the real world when you have these situations and you need to find angles or you need to find lengths of something or heights or distances. So let's do some examples. Okay, a reminder, if you didn't write this down already, PSF 166, 7 p.m. I think that's 2 weeks from tomorrow. 2 weeks from tomorrow, right? We got a full week of class next week, and then finals week, and this is Tuesday night of finals week. Okay, so here's a scenario. We set up this angle measuring device 70 feet from a tree. What do we want to know? We want to know the height of the tree. So we're going to use these triangle relationships, right triangle relationships, to help us find the height of the tree. So we need the triangle first. So can you sketch or imagine the triangle that we're going to use to solve this problem? How are we gonna superimpose a triangle into this situation to help us find the height of the tree? So will the base of the triangle be at the bottom of at the ground here? No. Where will it be? 3.5 above. Okay. So were you imagining that triangle right there? Cool. Okay. So here's what you do. We've got all these relationships. We've got the sine, cosine, and tangent, opposite. So this is going to be our hypotenuse, of course. Which side is this? Opposite or adjacent? It's adjacent to the angle that we have, right? 39. If we had this angle, it would be the opposite side. Okay? So then for 39, this is our opposite angle over here, or opposite side. Okay, so then you identify what you have and what you don't have that you want to know, and you pick the right relationship. So what do we have? We have this 70. What is 70? That's our adjacent side. What else do we have? Theta is? What do we want? We want opposite. Opposite's going to be the fast track to getting the height of the tree. So we have adjacent, we have the angle, we want opposite. Which of our trig relationships brings those three things together? So which one is the ratio of adjacent and opposite? That's tangent. So we're going to use tangent as the fastest track to getting the opposite side. So tangent of theta equals opposite over adjacent. So usually in these in the real world triangle problems, usually degrees is used, okay? Because that's what we commonly measure, in the field. This is how we measure angles. We use degrees most commonly. So set your calculator to degrees, and you're going to do the tangent of 39 equals opposite over 70. So then you plug in what you know, solve for what you don't, right? So we're going to solve for opposite, which would be, opposite would equal 70 tangent of 39. Make sure your calculator is set to degrees to give us that tangent. And is it 60 something? 56.8? 56.7? That's what I'm hearing. So the height of the tree is 56.7 feet. Right. We're not the base. So our base is up 3.5. I want the total height of the tree then. We're going to add 3.5. What was it, Walter? 60.2 feet. So what's the kind of the strategy here? You superimpose a right triangle into your situation, figure out which sides and angles you have, figure out the side or the angle that you want to solve for, and then identify which of the ratios get you. In this case, it was tangent. So the one that took the stuff that we wanted along with what we had, brought those together in a relationship so we could solve for the height. Questions on this example? Okay, this 39 degrees is an example of something they call angle of elevation. Okay, so angle up from horizontal. That's called angle of elevation. Can I erase? So there it is. So here's a boat example. So angle of elevation, up from horizontal. Angle of depression is an angle down from horizontal. The angle of depression is trickier because they can call it an angle of depression in a paragraph that they give you the information, and then when you're coming up with the picture, students are very often likely to make this angle the angle of depression. It's a very common mistake that students make. The angle of depression is the angle swept down from horizontal. Swept down from horizontal, which is not this. But when you start making the picture of the situation, it's very easy to stick in angle of depression in for that angle there. That's not it. It's the angle swept down from horizontal. Okay. Go. Solve it. So you got a boat. You got an anchor. It's let out 200 meters. The rope's angle of depression is 53 degrees. Assuming the ocean floor is level, what's the depth of the water? Go. No, I haven't been over there. Okay. So I figured it might lie in here for me. Stay the whole time.
Well, because you said nothing.
Well, there's the next class. I mean, it's the next class.
I had to think about before I went to my class. So they were there.
So make it on time.
Yeah.
Because then you- So I'll remind them to get there.
Well, the thing is, there might be a class that doesn't come.
It's there on Friday.
No. So,
But Monday it seems to be that's
yeah, well, there usually is on Friday too. So we just got like Friday.
I'll still tell them to make sure they're. I'll get there.
Yeah, they're all there.
Yeah, so that one that you asked about,
Yeah.
you know, scale.
Yeah, that's what I thought.
So they actually looking at that. Good. Well, their numbers. Yeah.
Whatever numbers you have on there is what I Oh, yeah. Yeah.
So they're just it's cool. They thought about it. Yeah. Cool. I just didn't have time to okay, but okay, who's up? Christian, get me started here.
I did. So first I just drew the triangle like next up the water.
Did you make the triangle here or here?
Right there.
This one?
Yep.
You made it here. Can you make it over here?
Yeah.
Sure. Okay, if you made the triangle here, it's fine. You just have to make sure your angle's right. So you made it over there, then what?
And then did sine 53 equals x over
So where's your 53 degree angle?
next to the boat.
Next to the boat. Is that a correct angle of depression? Swept down from horizontal. So you got it. That's 53 degrees. So if you do this here, if you make this triangle over here, and you put 53 there, you got it. It's not right. That's not an angle of depression. So yes, you can make this triangle, but then you have to know that that 53 is not this angle. It's this 53 would be this angle. So you'd have to take 90 minus, if you wanted to start with this angle here, You need 90 minus 53. 37. Okay, Christian, keep going.
Sure. So then sine of 53 equals x over square theta. Just x to x over 200.
And so you're saying x is which side of the triangle?
Now,
Opposite over hypotenuse. And how many meters deep?
159.73.
Agree? Set up the triangle, figure out what you know, what you don't know, find the right relationship that brings together those, either sine, cosine, or tangent, that brings together what you know and what you don't know. Yeah, Adam.
So the equal depression and angle of elevation, aren't they sort of reflections of each other? So
Yeah.
you were saying I would take 90 minus 53 to get 37 for if I did the triangle.
Yep.
But I can also just make an angle of elevation for the C4.
Yeah, totally. Yeah, so you don't usually talk about them both in the same context. But yes, they are the same value if you look at both of them in a certain context. It's what's called alternate interior angles, which are equal. Yeah, totally. Other questions? Okay, so let's do something a little more challenging here. So a cool use of this is you can measure the height of something really tall without having to. So with the tree example, that we had to measure this distance, right? So having this distance here and having the angle allowed us to get that height really easily. But so what if you can't get, how do we measure the distance to the center or the bottom of a mountain, right? So instead, we can set up something like this. So we can take a reading here, and this is 30 degrees. And then move 1,500 feet closer to the center, take another reading. Now it's 35 degrees. And so now we have a situation where we have enough information to figure out how tall it is. But it takes a little more ingenuity here. It's not just set up one thing and solve for the unknown and be done, like the easier ones we've done. So let's see see if we can make some progress on this. Okay? Take a minute and see what you can come up with. There's a hint. Did you start like that? That's what you need to do. Sine, cosine, or tangent? In general. In general. Sine, cosine, or tangent is going to apply here. She said tangent. So we're dealing with this what? This is adjacent side. We don't have either adjacent side, but we're dealing with adjacent sides and we're looking for opposite side. So yeah, tangent. So what is tangent of 30? How could we write tangent of 30? Matt, right here. You write tangent of 30 for this situation, for this picture? What would it be?
Opposite over adjacent.
Okay, tell me. So in the triangle with 30 degrees, what's the opposite? What's the adjacent?
Opposite y.
Why?
Adjacent is x plus 1500.
Is that a valid relationship here? Okay, Brandon, tell me about tangent of 35.
Opposite over adjacent. So y over x plus
Plus 1500?
or no, just x.
Just x. Yeah, y over x. Okay, so now we have two relationships and two variables that we need to solve. We want to solve for y. Okay, so we could take this one and solve this one for x, and we could plug it in down here. So for instance, let's see, we could cross multiply x. There's different ways to do this. X tangent 35 would equal y. So just, yeah, so we could take that, if that's y, and what can we do? We can substitute it in up there. And then we'd have an equation that just has x in it, and we could do the algebra and solve for x. And then once we had x, we can get, then we can use this here, what we just found, to get y. So whatever the value of x is, tangent 35 degrees would be y, and that'd be the height.